Alright guys, let's look at a little bit more percent composition. I'm not going to do all three of these at the top of the next page. You can take a look at them, but let's look at these. These are all going from the percent composition to the empirical formula, and I know that's something that you guys have had trouble with in the past. So let's do it this way. Let's get a sheet of paper and we'll go ahead and write this slightly larger on the back of, we can write it here. So, if we look, the first one is saying absorbic acid, otherwise known as vitamin C, is carbon, hydrogen, and oxygen. So definitely a organic molecule. If you think, we could probably figure out what its other name would be if instead of calling it absorbic acid, what it would be, like ethanoic acid or something like that. So the first thing we're going to do is we're going to write down the percentages, and even if they give us a mass, you can always just do it this way. We are going to write down the percentages, and we're saying, okay, if we had 100 grams, 40.92% would be, out of 100 grams, 40.92 grams, 4.58 grams, and 54.50 grams. Okay, so the next thing we do is we go to the periodic table and we look up the molar mass of carbon, 12 grams per mole, the molar mass of hydrogen, 1 gram per mole, and of oxygen, 16 grams per mole. You can go out more sig figs, like you could write hydrogen as 1.008, or use the more detailed value, but typically doing it this way will get us close enough to the answer. So what we're going to do now is we're going to divide row A, so let's label this row A, by row B. So this row, the next row is row A divided by row B. So 40.92 divided by 12, 3.41. 4.58 divided by 1, 4.58. And these are telling us the moles involved in 100 grams. And then 54.5 divided by 16. Oops, 54.5 divided by 16. There we go. 3.41. Well, okay, so right now you can already see that we have the same amount of moles of carbon as we do oxygen. So the next step is pick the lowest. And since these two are both the same, it doesn't really matter which one we pick. So we're going to pick 3.41, and we're going to divide C, row C, by the lowest. So we're going to do everything divided by 341. So we get 1. Let's see, 458 divided by 341. All right, so how do we go from here? This needs to be a whole number. All right, so let's write this as a fraction. This is approximately, or we could write it as, what would that be, 4/3. Okay, if I want to make this a whole number, the easiest way is going to be to multiply it by that denominator. So let's multiply everything by 3. Okay, so 1 times 3, that's 3. 4/3 times 3, that's 4. 1 times 3, that's 3. So we would have C3H4O. Right. Right, and so this one would be, if we were looking at it, we'd call it propus something because it's not got 2, but we would call it something with a propanol. Probably something like this with an extra, let's see, 1, 2, 2, 3, maybe a double bond here, so like that, and then there's an extra hydroxide attached to something. Maybe something like that. All right, so I would encourage you to go through the others, like the one I just did. See if you can't replicate that. Ask me questions in class if you have any questions on doing these empirical formulas. Okay, so moving on past empirical formulas, the next section is all of our Unit 5 stuff. Unit 5A and 5B, all about different types of equations, reactants and products. So reactants are the things, they're going to be the ones on the left-hand side, right? And they are the things you start with in a reaction. And the products are on the right side, and that's what you end up with. Or what you make. And so now we have this huge number of different equations that we should go through. And I'm going to go through a few of them. I'm not going to go through all of them. And we'll write the answers on a separate sheet so that you guys can see as I'm doing the work. I thought I had tucked a couple pieces in. All right, so let's just start with this first one, which is and it says, for all the following reactions, balance the reaction and identify the type of reaction as synthesis, decomposition, single replacement, double replacement, or combustion. There may actually be a neutralization or some in here, but we'll look for that. So let me write this guy out, Na3PO4. By the way, this is also an excellent time to practice your naming and transferring these equations into a sentence. So, for example, sodium phosphate combining with potassium hydroxide gives you sodium hydroxide and potassium phosphate. Okay, so let's just look. We've got a whole bunch of polyatomic ions here. We've got the phosphate ion and the hydroxide ion. And if you notice, they don't change very much. We haven't changed them at all. And there's pretty even there on both sides. What we have to worry about here in balancing is we have 3 sodiums here, so means we need 3 there. Well, we have 3 potassiums here, means we need 3 there. And so now that takes care of our 3 hydroxides and our 3 hydroxides, so that's balanced by putting a coefficient of 3 in front of the potassium hydroxide and a 3 in front of the sodium hydroxide. Now it's fully balanced. So if we're going to identify this, what's happened is the sodium and the potassium switch places. So this would be a double replacement. All right, the next one, magnesium chloride plus lithium carbonate. And sort of a reminder, sodium was a group 1 and potassium's a group 1, so they don't need numbers. Magnesium is a group 2 and lithium's a group 1, so they don't need numbers. If we were naming a transition element, we'd have to put the Roman numerals in. But these are all group 1 and 2, so we don't. All right, on the product side, we get magnesium carbonate and lithium chloride. Okay, so this is another double replacement where the magnesium and the lithium just switch spots. And I think it's helpful to go ahead and bracket your polyatomic ions, because if they stay together, it makes balancing easier if you treat them together. Okay, so let's look over here. Chlorine has 2 and lithium has 2. Well, over here, they only have 1 of each, but they're bonded together, so we can take care of that just by putting a 2 there, and now we are balanced. So that one was really straightforward. Okay, let's look a couple more down. Let's see, C6H12 plus O2 goes to CO2 plus H2O. That should be a dead giveaway as a combustion. We've got an organic plus an oxygen for our reactants, creating a carbon dioxide and a water for our products. So balancing, remember the only time this gets to be tricky is these odd numbers of oxygen. So let's just start with carbon. We're going to start, we say, well, there's 6 carbons here. 6 carbons here. So we need 6 here. So there's our first shot. We're going to try just putting 6 in front. And there's 12 hydrogens here. There's 2 here. So let's try another 6. And let's see, what does that do for our oxygens? We have 6 times 2, so that would be 12 oxygens here. And 6 times 1, or 6 oxygens here. So 12 and 6, that gives us 18. Good, that's an even number. So if I come over here, O2 to make 18, I'm just going to multiply that by a 9. So 9, so 1, 9, 6, and 6. And we'll just put those in, 9, 6, and 6, and this is definitely combustion. All right, let's do one more before we take a stopping point. And I'm going to probably leave most of these for you guys to do in terms of balancing. So the next one, Pb plus FeSO4 goes to PbSO4 Fe. Okay, so in this case, this guy's all by himself, and he comes along and he kicks out the iron and replaces him. So this would be a single replacement. Okay, so now let's go to our balancing. Bracket our polyatomic, and so if you look at it, there's no subscript here. Oops, no subscript. So this has to be, if SO4 is a -2, this has to be iron. We would write this as what? Iron 2 sulfate. And same over here. This is replacing with a lead. Oops, lead. Sorry, can't write today, guys. Lead 2 sulfate. And if you look at it, it's balanced. You don't have to do anything. So we can just go back to our equation and say that it's balanced. So if you guys take a look, the calcium carbonate in the next one, you should be able to identify that as a decomposition. The next one is a synthesis. And I'm going to leave the rest of these for you guys to do. We may cover some of them in class. But please review the rules at the bottom of your page on synthesis and decomposition, because in all these cases you've been given both the products and reactants, and sometimes this is you're going to have to determine what are the products to determine what the products are. for these last two equations. So, write a balanced equation showing the synthesis of hydrogen gas, which is diatomic, and oxygen gas, which is also diatomic, and it creates, what do you think? Probably water. So not balanced. There's two. That's balanced, but we've got to balance these. So now my oxygen is balanced, my hydrogen is not. There we go. Balanced. Right, last one, potassium carbonate. I notice a lot of you guys are getting confused with potassium and phosphorus. Potassium is a group 1 alkali metal, and it's a K. That's our symbol. And carbonate. Carbonate is a -2. Potassium's a +1, so we'd write it like that. K2CO3. And it decomposes. If you look back at your rules, one of the rules, I believe, number 2, says metal oxides and carbon dioxide react to form a carbonate. So if we want to do decomposition, a carbonate is going to decompose into a carbon dioxide and the metal oxide. Let's see, and in that case, we're balanced. All right. Keep reviewing through your packet, complete the rest of these that you didn't do, and we will continue in the next video.